Kindly, someone to confirm.
Yes, we can hear you.
That's nice. Now, in our last session, we introduced inferential analysis, and we also went ahead and do something on correlation analysis. Now, from correlation analysis, actually we were able to investigate and tell if there is a relationship or an association between two or more variables. And from that, we were able to tell the strength and the direction of that particular relationship. That is what we were doing last class. Now you realize at times we want to make a prediction. Suppose like the data set we are using, the consumption data set, we want to make a prediction on the consumption. Suppose the income increases. Now you realize with correlation, we are not able to do that. We are not able to actually do the prediction. We are only able to tell the relationship between the two in terms of the strength as well as the direction. Like what happens to one variable when the other one changes. That is what correlation is telling us, that if income increases, the consumption also increases. So it is telling us the direction of the relationship and the magnitude. Is it strong, weak, or moderate? But actually, we are not able to predict. We are not able to predict the consumption, suppose the income changes. Now today we are going to focus on regression analysis, because regression analysis addresses the prediction of one variable based on another variable. That is regression analysis. But before we even go further to talk about regression, let's load or rather import our data set to Excel. SPSS. Our data set is an Excel file. I've shared the data set, and those who will be watching this video on YouTube, the data set will be on the description. So to get the data set, we go to files, we go to file, then open, you select data. Now when you select data now, you need to navigate to the location where you have actually stored your data. Like for my case, I know my data is on the desktop. So I'll navigate to the desktop, and you need to make sure that the file type here is Excel type, is Excel file, and our data set is consumption 2. So I'll click open to load the data set. Now, of course, the first row is the variable names. So I'll click OK. And with some few seconds, my data set is loaded. So,
hello, excuse.
Yes.
Your data set.
I've shared the data set on the WhatsApp group.
Oh, so let me check.
Kindly download and load the data to your PC. Now, as we wait for Lawrence to download the data set and transfer it to his PC, let's just have a general discussion on regression analysis. Realize we are saying that regression analysis tries to actually addresses the issue of prediction of one variable based on another variable. Because yes, there's that relationship, but we want to use that relationship to now make a prediction. Now, I want to take you back to high school. Now, when you look at that equation of a straight line, we were saying that y represents the dependent variable and x represents the independent variable. This y is said to be dependent because it depends on x, such that as x changes, the value of y also changes. Now we were saying that m represents the gradient, or rather the slope. m was the slope. Now c represents the constant or the y-intercept, because this is the value of y when x is 0, because when we have x as 0, everything here cancel, it will be a 0, so we'll remain with c. So c is the y-intercept. C is the y-intercept. Now, this is the equation of a straight line. Now, the regression analysis is basically just this line, because in simple linear regression, you realize one of the assumptions is that the relationship is linear. So it is a straight line again, and this is the equation of a straight line. But now in regression, remember we discussed this in Excel, that is why I'm just trying to brush through. Now in regression, instead of having y representing the gradient, we have a coefficient, we have a symbol known as beta that we can use to represent that. So I'll have, let's say, okay, let me try to insert the symbols so that we are able to see that. So I'll have, let's say, beta. I'll say beta. Yes, Lawrence?
Yes, I've gotten it. Thank you.
Okay. Now let's call this we can call this beta 1, and we have another one here, we call it beta naught. Now let's have this other one here as let's say beta naught. I need to insert that as a subscript. So beta naught, and this one here as let's say beta 1. Now guys are coming for the class, eh? Okay, you say it's never too late until it's over. Now this is just a transformation of the equation of a straight line. But now we have y is equals to beta 1 x plus beta naught. So this is the basic function of a regression analysis, because this is a simple regression analysis, simple linear regression. It is simple because it has only one independent variable. Now from there, actually, I want us to talk about the types of variables in regression analysis, and more specifically, linear regression analysis. We have number one, what we call the dependent variable, which is at times called the outcome variable, or also the criteria variable. That is the variable y. Is actually the variable being predicted. This is the variable that is being predicted. And you realize in most of the cases, this variable will be denoted by y. In most of the cases, the variable which is being predicted is what is called the dependent, because its value is depending on x. Now that is the dependent variable. Now the other variable is used now to predict this dependent variable. Now this variable x, which is used to predict the variable y, is called the independent variable, or rather the predictor variable. And in most of the cases, you realize it will be denoted by x. It will be denoted by x. Now we have beta 1 and beta naught. Now in most of the cases, you realize we normally write this equation. In most of the cases, we will always start with the beta naught and then now have a beta 1. Now this beta naught, remember we are saying it was the y-intercept in the the equation of a straight line. Now this one here basically represents it's a constant. It's a constant. It will basically represent the value of the dependent variable when the independent variable is at 0. So this one is a constant. Now the beta 1 now is what is called the coefficient of the independent variable. Now this is the coefficient of x. It represents the change in y as a result of a unit change in x. Like if x changes, that change of x that results to a change in y is denoted by beta 1 here. Is represented by beta 1. So this is the coefficient of the independent variable. So this is the general equation. Now, to do regression analysis, you realize you will be provided with data set that represents the y values and another data set that represents the x values. Ours is to get the betas, that is the constant and the coefficient of the independent variable. So the software will assist us to have these values, these beta values, and will be able to predict y whenever x changes. That is now what we call simple linear regression. Now I want to talk about what we call multiple linear regression. We said in multiple linear regression, it is called multiple because it has more than one independent variables. So we have more than one x values. So it is a function like this one, or rather an equation like this one, is what we call multiple linear regression. It is multiple because we have more than one x values. It is multiple because we have more than one x values. You can see that. Now you realize in most of the cases, whenever we are trying to predict y, assuming in our case y is consumption, now we are predicting consumption based on income and family size. Now you realize in this equation, there could be some other factors which are not considered. Now those factors that are not considered that affect consumption need to be accounted for. Now to account for that, we normally have what we call an error term, epsilon, that now represents those factors that are not considered in the model. So that is why in most of the cases, actually you will always find that the regression function will always end up with this error term. It is called error term, meaning it represents all those other factors that were not considered in this model, but they actually affect the dependent variable y. The dependent variable y. It is also called noise or disturbance, the error term. So that is it. That is the general overview of regression analysis. Let's go to the real sweetness now on the software because it simplifies everything. I hope all of us have been able to load our data to SPSS. All of us have our data in SPSS. Another variable, gender, and gender is coded as 0 and 1. We will talk more about this when we get to regression with dummy variables, but I just want us to code our data. I mean, to tell SPSS what 0 represents and what 1 represents. So let's go to the variable view. I know we can all do that. And on gender here, we come to values. Now let's say 0 represents female. 0 represents female and 1 represents male. 1 represents male. Like that. So I just want us to code that. And we click OK. And we click OK. So we come back to variable view. And when we try to click on the value labels, you see now it is changing to the two categories in terms of character variable or rather strings. Saying it's female, male, and also, so forth like that. Now, that is our data set. So let's go now and do our regression analysis. We will start by doing simple linear regression analysis. Then we do multiple linear regression analysis. And lastly, we do regression analysis with dummy variables, both simple and multiple. Now, to do regression analysis, of course, we go to analyze. We go to analyze on the main menu bar. We go to analyze, then regression and linear. Regression, then linear. So when we click linear, you realize it will open the main linear regression window. It will open the main linear regression window. So from our correlation, we were able to see that there is a correlation or rather relationship or association between consumption and income. So let's try to predict consumption whenever income changes. So let's have consumption on the dependent variable and income on the independent variable. We've already talked about what independent and dependent variable are. Now you realize there is this drop down here representing method. Now we retain enter despite that there are other methods like stepwise remove, backward and forward. This enter method basically describe how the variable will be entered into the model as it is built. You know, the model is to be built, like those values are to be used in calculation. Those variables will be used to predict and determine them. So enter basically refer how those variables are going to be used in building the model. We'll talk about the other steps. Actually, they are very useful, like the stepwise, the remove, the backward, and forward. When I'll talk these some other time. We will have a session known as model building in SPSS, and we'll talk about that. So we'll retain enter there. We just retain enter. Then you realize there are other push buttons here that are here, and one of them is the statistics. Now, when we click statistics, there are several statistical options that we can include in our data set. Now, one of them is we need to check what we call the estimates. You see here there's the regression estimates. We always have to check on that so that we can obtain the regression coefficients. Now, regression coefficients are the betas we have been talking about. And remember, that is the most important thing that we want to obtain. So you always need to check on that and make sure that it is actually checked. Now, another thing that we need to check is the model fit. We need to check the model fit, because when you check the model fit, it will give us the R square and the adjusted R square. We'll talk about that, don't worry. Let's just mention the name. But the model fit will give us what we call the R square and adjusted R square. So whenever I run regression model, I always have to check the two. The others are just by the way, but you can add them, of course. Like we have descriptives. Now this one will give us descriptive statistics. Just like the same way, you'll go to analyze descriptive and then you go to descriptives. But we will have already done that before, so there's no need to check that. Another thing that you can check is what we call the part and partial correlation. Now, the part and partial correlation will give us three types of correlation. One, it will give us what we call the zero order correlation. It will give us the partial correlation and the semi-partial correlation. These are things we discussed when we were doing correlation analysis. Maybe those names are confusing you. But the zero order correlation is now the correlation between the two variables without any other variable as a control variable. That is now the zero order correlation. Now, partial correlation, we said it is a correlation between two variables, whilst we are holding controlling for another variable. That is what we said about partial correlation. And then we have the semi-partial correlation. So again, because we need correlation, we will not check on this. Now, collinearity diagnosis is just to check the collinearity. We'll discuss about that. Here we'll focus on just interpreting the regression analysis. Then in another session, we will come to check the assumption of regression analysis if they hold. So because we will be back, let's just continue by checking estimates and model fit. And we click continue. And we click continue. So from there now we can click OK and have our output. Basically, the analysis of regression will always give us three important tables. One of the tables is the summary model, or rather model summary. The second one is the ANOVA, and the third one is the coefficient table. by the way, when you click that table like I've did, it gives you room for editing and all that. We discussed about that. Now, one important thing is to know how to interpret the analysis, because I'm telling you, everyone can go and generate the output. It is just 3 steps, as you can see, but now be able to tell the analysis is what is most important. Now, I will not talk about everything as in these tables, but I'll talk about the most important things that you need to know, because in writing reports, there are those things that you should always include in that particular report. That is what we are focusing with here. Now, let's start with the summary model and realize actually these tables are given in the order they are to be interpreted. This is how you should interpret the table, as they are: model summary, ANOVA, coefficient, in that order. And I'll tell you why. Now, we start with model summary. Now, model summary gives us 2 important values. It is the R square and the adjusted R square. The R square and adjusted R square. Now, the adjusted R square is just a kind of standardization of the R square, because the R square value at times is kind biased. That is why now it is adjusted to adjusted R square. Now, the R square refers or is called the coefficient of determination. The value of adjusted R square, or rather the adjusted R square, is what is called the coefficient of determination. Now, generally, the coefficient of determination tells us the percentage of variation of the dependent variable as a result of the independent variable. I'll repeat. The coefficient of determination, that is the adjusted R square, will always tell us the percentage variation of the dependent variable as a result of the independent variable. What am I trying to say? I'm saying that on what percentage is Y changing because of X? That is it. Now, the value given here is in decimal. It is your role to convert it in terms of percentage before you can do your interpretation. And basically, we are taking this value and multiply it with 100. And when we multiply by 100, realize we are getting 65.4. We are getting 65.4. Guys, can you still hear me?
Yes, now we are hearing you. Can you come up again, please?
Sorry, there was a call and there was internet issue generally. So, as saying, it is your responsibility to convert the adjusted R square into percentage. And the simplest way is to take this value and multiply it with 100. So when I multiply this with 100, I'll have 65.4. I'll have 65.4%. I'll have 65.4%. Now, 65.4% is the percentage, or rather the value now of the adjusted R square in terms of percentage. Now, in my interpretation, I'll say the value of adjusted R square is 0.654, implying that 65.4% variation in consumption is as a result of income. I'll repeat. The value of adjusted R square is 65.4. Is 0.654, implying that 65.4% variation in consumption is being explained by income. The remaining The remaining 34.6% is explained by other factors not considered in this model. So that is interpretation of the model summary. As you write that report, I'm expecting you to say this one last time. From the model summary, the value of the adjusted R square is 65.4%. Is 65.4%. This implies that 65.4% variation in consumption is explained by income. The remaining 34.6% is explained by other factors not considered in this model. Guys, is that clear? Are you communicating?
Yes, we are communicating.
Perfect. So that is the model summary. Now, after we are done with the model summary, we go to the ANOVA. Now, the ANOVA, generally, before we go to interpretation, what ANOVA does is that it provides a test of the significance of the regression model. The ANOVA provides a test of the significance of the regression model. We are actually testing if the overall model is significant. Is this entire regression model statistical significant? That is what the ANOVA table is doing here. Now you realize there is we use what we call the F statistics. That generally the ANOVA is used to provide a test statistics of the significance of the regression model, like the entire model. Is this model statistical significant or not? Now, the test statistics here is what we call the F test, or rather the F ratio. There's some statistics behind that. We are not going to do that. We are just focusing on interpretation. Now, what we do, we look at the significance of the F statistics, or the significance of the ANOVA table. If this significance is less than 5%, that is, it is less than 0.05, then we conclude that our overall model is statistical significant. So in that report you are writing, I'll be like, from the ANOVA table, the significance of the F statistics is this value here, which is less than 5% significance level. This implies that the overall regression model is significant, or in other books they'll say is adequate, or another book will say fits the data set. From this, it is correct to say that our model is statistically significant. Mind you, this is the reason as to why I was telling you these interpretation flaws with the table as they are. You realize, if this regression model is not significant from the ANOVA table, we would have concluded that there's no better prediction that could be done from this model. So therefore, you realize we actually stop examining the results of the analysis at this point. What I'm saying is, if you realize, or rather you find that this model is not significant from the ANOVA table, if this model is not significant from the ANOVA table, then the question is, what are you even doing with the model, because it is not significant? So this model cannot make any good prediction, any better prediction. So therefore, we even stop examining our model at this point. We don't even go and interpret the coefficients, because the model is not significant in the first place. But now, because our model is significant, we'll now go for the coefficients. Now, because there are a lot of things I've not included, I just want to focus on getting the basics, or rather the foundation. We have the coefficients here. The coefficients. That is the beta coefficients here. This one is the constant we are talking about, and this one is the income. This is the constant, and this is the income. So if we go back to our model, this one will be, the model will be consumption is equals to 170.45 plus 0.003 income. That is the model. Now, when it comes to the coefficients, there are two important factors that you need to always interpret. Number one, it is the coefficients themselves here. That is the constant and the coefficient of the independent variable and the significance of the coefficients. Very important. Now, the significance of the coefficients is tested by the t-test. But now, instead of using the t value itself to test the significance, we'll just use the significance value. Now, this is what we'll say. For me, I'll always write the model and say, from the coefficients table, the regression equation will be, consumption is equals to 170.45 plus 0.003 income. This implies that holding income constant at 0, the consumption is 170.45, because we said the constant represents the value of the dependent variable when the independent variable is held constant at 0. Now, suppose income was measured in Kenyan shillings. Suppose it's measured in Kenyan shillings or in dollars. Let's say in dollars. So $1 increase will increase the consumption by this. We said that this coefficient represents the change in the dependent variable as a result of the independent variable. So 0.003 represents the change in consumption as a result of change in income. Now, suppose our income is measured in dollars. I'll now start operation and say, from the coefficients table, the regression equation is given by consumption is equals to 170.445 plus 0.003 income. This implies that holding income constant at 0, the consumption is 170.445 units. $1 increase in consumption, $1 increase in income increases the consumption by 0.003. The significance value of the coefficient of income is this, that is less than 0.001, which is less than 5% significance level, and therefore income is a significant factor affecting consumption. I'll say that for the last time. From the coefficient table, the regression equation will be given by consumption is equals to 170.445 plus 0.003 income. This implies that holding income constant at 0, consumption is 170.445. $1 increase in income increases consumption by 0.003. The significance of the coefficient of income is 0.000, which is less than 5% significance level. Therefore, at 5% significant level, income is a significant factor affecting consumption. I don't know if that is clear. Guys, are we communicating?
Yes, we are communicating.
Perfect. Now, the reason as to why someone was asking maybe, why is it that I'm saying a unit increase in income increases consumption? It is based on the sign of the coefficient. That is the coefficient of income here is positive. So if it is positive, it means it will be an increment rather than a decrease when it is negative. So you always have to consider the sign before you do your interpretation. So that is simple linear regression. Now you realize when we do multiple, we are just increasing the number of variables. So I want us to do now multiple, and then we will do the interpretation. You now will be doing the interpretation. And today I'll be mentioning names. I'll be mentioning names as they appear from my list. So if you be mentioned, lucky you. So let's do consumption as the dependent variable, income, and now family size. But we have net worth as well. So we can do any. So we go to analyze, then we go to regression analysis, we go to linear. Now we include net worth. Let's leave everything else as it is and click OK. And here now we have our output. Okay. So can someone volunteer to interpret the first the summary model? Someone to please try this. Yes, Lawrence, carry on.
Yes, I can try.
Okay.
So in the model summary, the value adjusted R variation is 0.877%, implying that 87.7% percentage variation in consumption is being explained by income and net wealth. Yes, that's my opinion.
So that is good, Lawrence. That is good. Lawrence is saying that from the summary model, the value of adjusted R square is 0.877, implying that 87.7% variation in consumption is being explained by net wealth and income. That is good. And I was expecting him to continue and say the remaining 12.3% is explained by other factors not considered in this model. Always have that statement to show what you didn't take care of in your model. So that is good. Another person to do ANOVA, a volunteer. Mr. Morrison, kindly proceed.
Yes, let me try ANOVA.
Yes.
Now you can see that the significance level is 0.000. So when you compare that figure with the confidence, with the significant level of 0.05, we find that it's less. So we conclude that our analysis is significant.
That is good attempt, Mr. Morrison. That is good. That is very good. That is good. Only that I'd love if you change the word analysis that specify that our regression model, because it is now the type of analysis is actually specifically regression. So Mr. Morrison is correct because he's saying from the ANOVA table, the significance of the F test is 0.000, which is less than 5% significance level. This implies that our overall model is significant. Another person can say, this implies that our regression model is significant. The model is adequate. In other books, they say it is test for adequacy of the model. Or you can even say, this implies that our model fits the data set. Still mean the same. It's up to you. As you read several books, you'll see all those words, and it's nice. Coefficients. I see now today boys are really active in this class, unlike the other one. I like this. So who is interpreting coefficients? Yes, a star.
Okay, from the coefficient table, the regression equation is consumption is equals to 155.446 plus 0.001 income plus 3.641 net wealth. Holding income and net wealth constant at 0, consumption is 155.446. 1 unit increase of income will increase consumption by 0.001, and 1 unit of net wealth will increase consumption by 3.641. The significance value of the coefficient of income is 0.000, which is less than 0.05. Therefore, at 5% significance level, income is a significant factor affecting consumption. Then the significant value of the coefficient of net wealth is 0.000, which is again less than 0.05. Hence, at 5% significance level, net wealth is a significant factor affecting consumption.
A star never disappoints me. Never. I mean, that is what I would have said. That is perfect. Awesome. Now, that is it. Now you realize, as you interpret this, things I've learned with time is that more so when it comes to interpreting the coefficients, take into consideration the units of measurement. As you do actual analysis into the real life and all that, you will always, suppose you are given data, there is what we call data documentation. You are given an explanation on what the data is representing, or rather presenting. So what you do, you need to check on the documentation to know the units of measurements. Here we don't have value labels because we are importing this from. Realize maybe it was income in dollars. Consumption in this. Those measurements, those units of measurements, they're very important when we are interpreting our coefficients, such that instead of always saying a unit increase in this, a unit increase in that, quote those coefficients. Suppose income was measured in dollars, and maybe net wealth was also measured in dollars. So I'm expecting you to say a dollar increase in income increases net wealth by this. Okay, let's assume consumption is measured in kilograms. Maybe you're consuming let's say certain rice, the kgs of rice you are consuming. Now that is very many example. But let's say it's measured in kilograms. For the purpose of explaining this, I'm expecting you to say a dollar increase in income increases consumption by 0.001 kilograms. So take note of those units while explaining this. Any question up to that point? Any question? Any point that is not clear? Any concern? No concern, no question. Good. Now, I want us to go
I have a question.
Kindly ask. Yes, Esther.
Okay, like from the coefficients table.
Yes.
Are we not talking about the hypothesis?
Okay. You realize one thing. I know, Esther, you are a statistician. I too am a statistician. Now, there is a lot of statistics. That is behind all this. You see, I've not even talked about the standard error. I've not even talked about the beta standard coefficients. I've not even talked about the t value and all that. Because I'm trying to make it simple the way you'll present it in a table. Now, the fact is that I'm interpreting as if I'm writing a report. So that statistics that you have, you need to put it at the back of your mind to help you do the interpretation. Yesterday, the statistics you are asking, we are actually using it here. Because whenever you're saying that the significance of income is 0.000, which is less than 5% significance level. Therefore, income is a significant factor affecting consumption. That statement is a conclusion of a hypothesis. So it is as if you have tested the hypothesis at the back of your mind. Because imagine you are writing all that statistics on that report, you end up writing, a lot of pages. So the hypothesis and the statistics is there, but it is to assist you in interpretation. Because imagine I'm saying this, from the income, the significance of the income is 0.005. Since the significance is 0.005, which is less than 5% significance level, we reject the null hypothesis that income is not a significant factor affecting consumption. This means that we fail to reject the alternative hypothesis that income is a significant factor affecting consumption and conclude that income is a significant factor affecting consumption. Sounds a lot of repetition and all that. So the hypothesis is there. It will always be there. But keep that at the back of your mind, right? Make it short. Remember, assuming you are presenting this to Mutahi Kagwe, this is now COVID-19, and this is now quarantine. Income is quarantine, and net wealth is social distancing. So we have concluded that net wealth, social distancing and quarantine are significant factors that can control the spread of COVID-19. So you are the analyst. You have done that analysis. Imagine rejecting the null hypothesis, failing to reject the alternative and all that. You are writing this report to someone who have never stepped in a statistical class. Actually, if I'm writing this report to Kagwe, I won't even bother about the coefficient as such. I'll just tell him that from the analysis, it can be concluded that quarantine is a significant factor controlling COVID-19. As well, social distancing is a significant factor that can control the spread of COVID-19. And we'll read that to Kenyans. And Kenyans, because that will be now the rule. There is quarantine and there is social distancing. You see that? But now you as an analyst, you have considered a lot of things. You have tested the hypothesis, rejecting and failing to reject and come up with the final conclusion. So basically, Esther, there's a difference of academic research and a real life research. So when you're doing it for academic purpose, maybe a class assignment and all that, you can include all those statistics and show your lecturers that you know statistics. But when it comes to the real ground now, when I say ground vitu ni different, make it short. Whoever is reading your report might have never even studied in a statistical class into a criminology. I think Esther have answered your question.
Yeah, thank you.
Perfect. So I was saying this reminds me of one question I need to ask you. Initially, we were looking at we were doing a simple linear regression, and when we were doing the simple linear regression, you realize that we were having consumption and income. We are having consumption and income, and the output is here. Income was statistical significant. The value of R square is that. ANOVA is that. Now we have multiple, and we have income and net wealth. Now the question is does increasing net wealth really affect this model? Like, does it really affect the prediction of consumption? What do you think? Who can try? Do you think that increasing net wealth brings a more explanation of consumption, like brings more predictive power of the model? What do you think, guys? Because look here, you can look, just check all the tables. Net wealth is significance, income still significance. The ANOVA table shows also its significance, like Morrison has interpreted that. The R square now is also 87%, like Lawrence has interpreted that. Now look at the ANOVA table. The model summary. The model summary. You can see now it's 65%, the F and all that. So does increasing in net wealth really affecting the model? Now to answer that question, we look at the value of the R square. Remember, when we were doing interpretation, we were interpreting using the adjusted R square. But now we are looking at the R square. Look at the R square before adding net wealth and after adding net wealth. If the value of R square changes significantly, it means that now the added variable is actually improving the model. If there is a change in the R square, then it shows that the model is actually adding the predictive power of the variable. The independent variable added is actually adding the predictive power of the model. And you can see now our value is 884, and initially it was 664. So net wealth, yes, we need to include it in our model. Any other question? Before we wind up with introducing something to do with dummy variables. Any question? Any point that is not clear? Okay. Now, let's finish this by looking at regression analysis with dummy variables. Now, this is a case whereby, of course, our dependent variable is continuous. It is quantitative in nature. But now the dependent variable is categorical. The independent variable is categorical, such as gender. How do we do such a model, or how do we interpret it? Because is the interpretation the same or not? Now, this is a case where we say it is a regression analysis with dummy variables. Now, dummy variables, also known as indicator variables or just dummy, is one set of variable that takes only two values, that is 0 and 1. You can see our values are 0 and 1. So it only takes two values, 0 and 1. Now, this 0 and 1 is used to indicate the absence or the presence of some categorical effect that might be expected to shift the outcome. I mean, when I put, or rather I have female represented as 0 and male represented as 1, it therefore means that as we fit our model, one category of this variable will be absent, while the other one will be present. And that now will affect the model and its output. So you realize that they will be shifting of the outcome based on those categories. That is, it is like, in simple terms, it is like I'm not including the effect of female in doing analysis, but I'm only having that of male. There is now the dummy variables. Now the question is, what if we have several categories? Still we'll use the dummy variables. But the point is that even if the categories are more than 2, the values that you can only assign is 0 and 1. So if I have 4 categories, one category will take 1, while the rest will take 0s. And then they'll alternate like that. So before I confuse you, because I don't want to confuse you, let's just focus on gender, which has only 2 categories. Now you realize the female is coded 1 and the male is coded, the female is coded 0 and the male is coded 1. Which means that the effect of female as a category will not be there in the model, while that of male will be there. So how do we interpret such a model? So let's run the model, and then now we do the interpretation. So to run the model, of course, we go to Analyze, still Regression Analysis, and still Linear. Now let's take all these variables out. Let's take all these variables out and have gender there. And have gender. The rule remains enter, and the statistics, all that, we don't include that. We just need to make sure that we have the estimates and the model fits. So continue and click OK. And click OK. And click OK. Now I have my model summary. Again, I have my ANOVA table, and I have my coefficients. Now, I'll not interpret model summary, because the interpretation of model summary will just remain as it is in the other cases. As well, I'll not interpret ANOVA, but I'll interpret coefficients. Now, because we are learning, I'll interpret it so that you can get to understand how we interpret the dummies. But actually, based on the rule of the thumb, we are not even supposed to bother about the coefficient. We are actually actually we need to forget about this model. Why? Because of the ANOVA table. Our model is not statistically significant. So what are we struggling to interpret where the model is actually not significant? So I would have stopped here. And actually the model is really not significant, because look at the value of adjusted R square. By the way, let me tell you one thing. Okay, this is a hypothetical data. I generated the data using random between in Excel. So it's a hypothetical data, more so on the gender. And I'm telling you, since I started doing analysis for the real data set, I've never obtained an R square of 0, 0, adjusted R square. This model is really insignificant. But anyway, let's focus on interpreting the dummies. Let's focus on interpreting the dummies. Now you realize we have our female coded as 0 and our male coded as 1. Now I want to explain this model, actually to just explain the overall model, and by the time I finish, you would have actually come up with the interpretation on your own. Suppose I just want to write the model now in Word, where we are having this model. This is what I want to do. Okay, I have my, let's say X now is gender, but I can just say gender. That is gender. Okay, what is the value? What is the value of the coefficient of gender? 3.89. So it is 3.89 gender. Okay, just like that. Then what is the value here? What is the value here? The value is 32878. Like that. Now, my gender here, sorry for that. My gender here is such that males are coded as, I just need to confirm that. The males are coded as 1s and the female 0. Yeah, the female is 0 and the males is 1. Now, assuming, let's start with the first case. Assuming here now the gender is female. The gender is female. So when the gender is female, it will be like I multiply that now with a 0 because it is female. And realize at the end of the day, I'll have my consumption. Let's say Y represent consumption as 32.878 because it is female. Because it is female. Now, assuming now it was a male. All this, but now it's a male. What will we have at the end of the day? Now here we have 1. Now we have 1. And this is a male. Now you realize my consumption will be, we are adding there. Mathematicians, what are we having? Let's just discard the decimal and say it is 31, like that, point something. Right? Or let's say 32 point something. Now realize this one was for female because it is coded 0, and this one was for male because it is 1. So how do we interpret that? How do you interpret that? Now, one thing that you know for sure from this first set here is that this constant, the constant represents the consumption for female. I know you can all see that now, that this constant, because this is the value of the constant, so the constant represents the consumption for female. Now what about this? Yes, because these are now what we need to interpret. We need to interpret this, the coefficient, that is the constant, and now this other coefficient. So we are saying, we are agreeing that this constant here is actually the consumption for female that we have computed here, because female is coded as 0. Now this other constant here, the value, you realize that whenever it is a male, it will increase from that of female by this, and we end up having this. So which means this other constant represents what is more when one is a male. What is more when one is a male. I hope now you are getting the picture. Now one thing you need to take note is that this computation of the constants, of the coefficients, is in terms of average. So it therefore means that the average consumption for female is this, while that average consumption for male is more by this. I don't know you're getting it. In some other books, they call this as the average difference in consumption for males to female is this. And that is how you interpret. This was not the mathematics behind, but that is how you interpret. So I'll come and say now from my output, the one that is not, the one that was being held constant 0 is what is represented by this. Now the one that is coded 1 is this more, but it could be less when the sign of this coefficient here was negative. So this is how I'll say, from the coefficients table, the average consumption for women, the average consumption for female is 328.78. Being a male increases the average consumption by 3.891. The significance value of the average difference is 0.335, which is greater than 5% significance level, implying that being a male does not significantly increase the consumption. That is one perfect interpretation you can give. Another one, just the same now in different words, is, that the average consumption for female is 328.78. The average difference of consumption of male to female is 3.891, implying that the average consumption shifts by 3.891 from female to male. That statement means that it increases from male to female. From female to male. Hope I'm not confusing. Just means that it is increasing. It's all that we're trying to play with the problem. I'm not an English guy or something. But that statement implies that. Then you come to the statistical significance and you say, since it is greater than 5% significance level, so therefore it means that there is no significant shift in consumption from female to male. So you're seeing I'm using the word shift. The other time I was using increase. It is up to you now how you put it. But the first one was short and clear, that the average consumption for female is 328.78. The average difference of consumption of female to male is 3.891, implying that being a male increases the average consumption by 3.891. The significance value of the average difference in consumption is 0.27, which is greater than 5% significant level, implying that at 5% significant level, there is no significant difference in consumption from female to male. Guys, is that clear? Because in most of the cases, people make a mistake of interpreting this just like any other variable. You will hear someone saying, and it is a categorical variable like gender, saying that they have, imagine someone is saying this, and now I'm trying to imagine how you even put it, because someone will be like, I know this is wrong anyway. From the coefficient table, the consumption, hold gender constant at 0. The consumption is 328.780. A unit increase in gender increases the consumption. A unit increase in gender. On a serious note, a unit increase in gender. Now, just take the first statement saying hold the gender constant at 0. So it means that person is neither male or a female. Like, the person is not a male or a female. So you're holding constant. So where is, and in our data set we have only male and female. So that is the regression analysis with dummy variables. Whatever you are taking as reference is what is called the reference category. And in our case, you realize our reference category is a female. Whatever we are doing, we are referring to that. So that is regression analysis with dummy variables. So if there were several, we could have one coded as, we have one coded as 1 and the rest is 0. So we are giving reference to this particular one. I'll be sharing some notes on regression analysis. They are just general statistics, not as such. But they'll open, for Esther who was asking the hypotheses and all that, we'll see those things there. I'll also share an assignment. So good night.